Okay, so in chapter 9, we're gonna learn about composites. So in this chapter, we're gonna learn about composites, and composites usually characterized with their high strength to weight ratio or high stiffness to weight ratios. So composites are generally used in aerospace industries and automotive industries because we can obtain strong and lightweight materials by mixing different types of materials, what we call composites. And in this chapter, we're gonna learn about different types of composites and the reinforcing fibers, and then how it actually improves the mechanical properties of the matrix material. So there is matrix and there is the fibers, reinforcing fibers. Matrix is usually plastics but can be metals and ceramics. And we're gonna learn about different matrix and different fibers or reinforcing materials. Okay, let's start. So what is actually a composite, right? So it is actually combination of two or more. It doesn't have to be just combination of two or more distinct and insoluble phases with a recognizable interface. So these different parts of the material is gonna be easily determined because they are distinct, chemically different, and there is an obvious interface between the two regions. Okay, so the reason why we mix two or more materials is that because this way we can obtain properties that are superior to those of the individual components acting independently. So what can be these combinations, how we can combine different types of materials? We can combine reinforcing fibers with polymer matrix, metal matrix, ceramic matrix, and based on that we divide composite to 3 different types. And as I said, composites are actually found applications in aircraft, space vehicles, satellites, offshore structures, piping, electronics, automobiles, boats, and especially sporting goods like tennis rackets, baseball bats, etc. So today's aircrafts, in this example we see Boeing Dreamliner, 50% composite by weight. Of course, not a composite cannot be used in everywhere because in some areas we need electrical thermal conductivities, so we use metal alloys like aluminum alloys, but most of it is composite, and this provides again lightweight and high strength to weight ratio. Basically we see carbon laminates and we see sandwich composites. So when we are mixing two different materials, two or more, we can mix them in variety of different shapes, so each constituent can have a different shape to optimize basically the performance. So we also see fiberglass. Okay, so as you can see, composite is used in aircrafts. So first let's look at reinforced plastics. This is the most commonly used composites, so it is important to cover this topic. So We call these reinforced plastics or polymer matrix composites or fiber reinforced plastics. Basically what we have is a matrix, a continuous phase, and we put fibers like this, right? So these are the reinforcing phase fibers, and this is matrix, and these are fibers. So fibers are discontinuous, dispersed. It is very important to be able to homogeneously distribute the fibers or other type of reinforcing elements. This way we get a homogeneous distribution of properties, and polymer can be epoxy or any other type of polymer. Okay, so we're gonna see those. And we know the polymers providing the lightweight, but they are not strong. So by putting the fibers, we obtain a material that is lightweight, and fibers are providing the strength and stiffness. This way, mixing two of these materials, giving us high specific strength and high specific stiffness. This also increases the fatigue resistance, toughness, and creep resistance compared to just non-reinforced plastics, basically. So reinforcing material usually in the form of fibers, but it doesn't have to be. It can be particles. Okay, it can be particles, short fibers, long fibers, flakes. And as you can see in these images here, we have particles in a composite. Of course, they are not showing the particles, why I don't understand. But think about particles are there, homogeneously distributed in a polymer matrix. There can be short, like chopped fibers, all homogeneously distributed, or there can be long fibers that are distributed in the structure. And these long fibers also can be called continuous fibers, can be aligned in different angles, like 0 degree, 45 degree, again 90 degree, let's say 45 degree. So depending on how they are aligned in the structure, properties enhance only in that direction, not in the transverse direction. Okay, so these layers can also be put on top of each other, forming laminates, and there are foam structures in between two different materials, and we can put in. So as you can see, the configurations of how we mix two different materials are changing. Okay, so there is honeycomb structure in between two metal plates, maybe. Okay, so different ways of mixing two different types of material. So for fiber reinforced plastics, usually the fiber percentage is between 10 to 60%, and fibers themselves do not have any structural volume, and by mixing with polymers we combine the advantages of two materials, basically. And as I said, polymer is less strong and stiff than fibers, but it is tougher and chemically inert, and the structural enhancement achieved only in the aligned direction of these fibers, not in the transverse direction. So if we look at the reinforcing fibers, what type of fibers are used to reinforce plastics? So we can see that glass fibers, carbon fibers, boron fibers, aramids, or known as its trade name Kevlar. And there are also other fibers important, like nylon, silicon carbide, silicon nitride. As you can see, all these materials we learn, and these can be shaped in the form of fibers and can be used as reinforcing materials. What about the matrix? Matrix can be thermosets, thermoplastics, and metals and ceramics. So usually for thermosets, this is epoxy and polyester, and thermoplastics, there are different type of thermoplastics that can be used, and metals, aluminum matrix, aluminum oxide, and the fibers are aluminum oxide, silicon carbide, and the matrix is like magnesium, aluminum, titanium. Ceramics can be silicon carbide, silicon nitride, etc. So in this figure we are seeing specific tensile strength and specific tensile modulus, basically strength over density and modulus over density ratios for various fiber that we use to reinforce plastics. So some of them are listed with their trade names, and we might not be able to obtain their composition, but we know Kevlar, and you see how high it is, strength to density ratios, and different types of reinforcing glasses, graphite, boron, aluminum fibers, titanium, steel. So all those information are listed, and we can compare different types of fibers. So if we look at reinforcing fibers, we have seen glass, carbon, ceramic, aramid or Kevlar, and boron fibers. And now let's look at each of these. And again, I suggest you guys, because I'm giving you videos from YouTube that shows how some of these like glass and carbon fibers are actually made, and you can see the whole procedure there. Okay, so I suggest you guys to watch those to learn more. So glass fibers are most widely used ones and the least expensive. That's why it is very commonly used. And these composites contain from a range of 30 to 60% glass fibers, and the rest is basically polymer, right? So how they do these glass fibers? They are making them by drawing molten glass through small openings in a die. So if you watch the video, you will see. Okay, so basically the fibers need to be treated with certain chemicals we call silane, which is a silicon hydride. The reason they treat the fibers with that is because this way they can provide better interaction between the fibers and the matrix, because if fibers and matrix are not actually interact with each other very nicely, what happens? The stress transformation from the matrix to the fiber is not happening. Okay, so the interface is very important between the fibers and the matrix, because at the end, when we apply stress to the matrix, it has to transfer the stress to the fibers, because fibers are the ones that are carrying all these stresses, right? That is what we want. We want the fibers to carry the stress, not the matrix. That's the whole idea. So there are different types of glass fibers. And E-type, which is a calcium alumina borosilicate glass. S-type, a magnesia aluminosilicate glass. ECR type, that is high performance glass fibers, higher resistance to elevated temperatures and acid corrosion than E-glass. So depending on what type of application that you're gonna use them, you can choose one of these different glass fibers. Basically what changes is the composition is changing. Okay. carbon fibers more expensive than glass fibers, but it provides great properties like low density, high strength, high stiffness. So how we make carbon fibers? So first you need a carbon source, okay, and this carbon source come from, of course, organic molecules like polyacrylonitrile, PAN. And what happens is that PAN fibers, they are exposed to high temperatures in oxygen-free environment, and what happens is that all non-carbon atoms are expelled from the structure. Once this is achieved, and fibers then are woven into a fabric or can be combined with other materials that can be molded into desired shapes and sizes. There are also graphite fibers which are conductive and make it possible to enhance electrical and thermal conductivity of the matrix, the plastic. That can be used in electromagnetic radio frequency shielding, lightning strike protection. So this one also has different areas. Ceramic fibers. Of course, ceramics, we know they can be suitable for high temperature applications, and ceramic fibers usually put into metal matrix. And of course, we cannot have by difficulty of processing them. They can be more like chopped fibers or particles. So these fibers have low elongation, which we expect, right? They are not ductile, low thermal conductivity, good chemical resistance, in addition to being suitable for high temperature applications. And there is alumina, silica, boric oxide, different type of ceramic fibers like silicon carbide are possible. And what about polymer fibers, right? And we can make fibers out of polymers, and this can be nylon, aramid, and different types, okay? And the most common one maybe you have heard is Kevlar. This is the toughest. The reason is because remember how polymers are made, right? There is strong covalent bond in the chain, but in between the chains there is weak forces, right? But when it comes to Kevlar, those are not weak bonds between the chains, like more strong hydrogen bonds and other covalent bonds, which make them very strong. So it has high specific strength. And again, there is a video for Kevlar I want you guys to watch to learn more. And then, of course, compared to brittle fibers, they have higher toughness. So another polymer fiber is polyethylene fibers. Spectra is the trade name again, like Kevlar. And this one has ultra high molecular weight and high molecular chain orientation, better abrasion resistance, flexural fatigue strength than compared to aramid fibers, low density, higher specific strength, specific stiffness compared to Kevlar. But the problem is they have low melting point, poor adhesion to the matrix basically. So poor adhesion, again, as I said, there should be a good strong bonding between the fiber and the matrix themselves so that we can obtain the best out of the material. Okay, so next is boron fibers. And these are basically just fibers of tungsten and with a layer of boron that is deposited on top with different techniques. One of them is CVD, what we call chemical vapor deposition. In a certain atmospheric environment at high temperatures, boron is deposited on the surface of the tungsten filament. And of course, these are providing high strength, stiffness, resistance to high temperatures, but tungsten is heavy. That's why the boron fibers are heavy, and also boron is expensive. So in this table, we are able to compare the properties of different fibers like boron, carbon fibers, glass fibers, Kevlar, and other fibers with their trade name alumina, silicon nitride, silicon carbide. And we see that the cost of boron fibers is the highest, most expensive, and glass fibers are lowest, and carbon fibers are a little bit more expensive than the glass fibers, but still we can count it as low compared to other fibers, boron, alumina, silicon carbide. We see their elastic moduluses, we see their strength, and I can see that strongest ones are actually glass fibers, right? And so this is showing us a cross section of a tennis racket. As I told you guys, in sporting goods, composites are commonly used. And when they look under the microscope, you can see the layers, different layers of reinforcing materials and the matrix. Like, you don't have to just put Kevlar in a matrix, you can put two different fibers in a matrix, right? We are seeing graphite together with Kevlar and combined with probably a polymer matrix, providing the lightweight and strength together. And we also see the structure of boron fiber, reinforced composite. We see the matrix, and we see the tungsten core, the fiber, and the deposited boron on top of it. The fiber size and the length is very important in how much enhancement you can get out of that material, right? So they can be short and long. So short ones are discontinuous, long ones are continuous. So how do we define short fiber and long fiber? So if the mechanical properties improve as a result of increasing the fiber length, it is called short fiber. So that means as you keep increasing, you keep getting better and better results. That means you have a short fiber. If you keep elongating the fiber and still not getting improvement, that means you already have a long fiber. Okay, so after certain lengths, then we don't get an increase in the improvement as we increase the fiber length. That's one we call the long fiber. So fibers can be different configurations, morphologies, like they can be chopped, particles, flakes, a continuous rowing, like twisted strands, woven fabric, yarn, twisted strands, and mats of various combinations. Okay. What about the matrix? So matrix, as we said, it can be ceramic, polymer, metal. What is the role of the matrix? Is basically hold the fibers in place and make sure to transfer the stress, the applied stress, to them. to the fibers, so the fibers can carry the load. That is the whole goal. You want the fibers to handle the stresses, not the matrix. And it also protects the fibers against damage and environmentally caused chemical degradation. Because of the ductility and the toughness of the plastic matrix, it also provides a slow propagation of the cracks, so preventing sudden failure of the materials. And we said a matrix can be thermoplastic, thermoset, and the most common are the epoxies. Nearly 80% of all reinforced plastics. And there is also polyesters, which are less expensive than epoxies. But many other polymers can be used as matrix, depending on what type of application, in which type of application you're gonna use them. And remember, the thermosets have better strength values compared to thermoplastics. So mechanical and physical properties of reinforced polymers depend strongly on what type of fibers you have, what is the shape, orientation of the reinforcing fibers, and their length, and how much we have them inside the material, their volume fraction, all determines the behavior, the properties of the overall composite. So as I told you guys, the interaction between the interfacial bond strength in between the fiber and the composite very important, because if there is a weak bonding, you cannot transfer the stress properly to the fibers, and what happens, there is fiber pull out or delamination of the composites. So we talked about glass fibers being treated with silane in order to enhance this interfacial bond. And the properties of composites, they are highly anisotropic, meaning you achieve strength and stiffness enhancement only at a certain direction, in the direction that is the fibers aligned. So it all depends on what type of properties you want to achieve. So that will change the type of reinforcing material. Like, do you want to achieve resistance to fatigue, creep, wear, and how much you need to put in. And of course, these are all experimentally determined, right? So in this figure, we are seeing the effect of the type of fiber on the properties of nylon. So compared to short fibers, we see that long fibers provide better enhancement in tensile strength, impact strength, and flexural modulus of the composite is the best when we use carbon fibers and compared to glass fibers. And again, we are seeing flexural strength and flexural modulus. Carbon fibers are performing the best in nylon. And seems like long fibers are better reinforcements compared to short fibers. In these microscopic images, we are seeing the fractured surface of glass fiber reinforced epoxy. So you guys are seeing, this is the matrix, and these are randomly oriented fibers within the structure and their sizes we are seeing. Of course, they didn't provide a scale here, but the figure description says the fibers are 10 micrometer in diameter and have a random orientation. So we also see fracture surface of graphite fiber reinforced epoxy composite. In this case, we are seeing the fibers are in bundles, not individually dispersed. They are the bundles, and all of these bundles are aligned in the same direction in the structure, and they are again between 9 to 11 micrometer in diameter. So as I told you, the property enhancement are achieved in the direction of alignment of the fibers. So all types of properties, right? Creep resistance, thermal electrical conductivity, thermal expansion, all those are anisotropic, not just the tensile strength. And in the transverse direction though, we don't obtain the same enhancement. And this six figure shows us that. Okay, so here we see tensile strength versus the glass fiber content, and we see how the enhancement is achieved based on the alignment. The best performance we obtained when we align the fibers in only one direction, we call it unidirectional, and when we test the material along the direction of the fiber, that's when we obtain the best strength values. So what are the application areas of reinforced plastics? Wide range, right? Acid resistant tank, boats, aircraft, electrical equipment, sporting goods, high temperature applications, commercial and military aircraft, and rocket components, helicopter blades, helmets, golf club shafts, and tennis rackets, fishing rods. Just some of the examples. Of course, there is a wide range of application areas for composites. So this is an image of a sailboard and a cross section of it. We're going to look in through this section, and we are seeing that, okay? We are seeing inside. We are seeing that composites are used, and we are seeing layers of different types of composites are being used in different directions. So there is let me see where the composites are. So there is carbon and Kevlar fiber strips in different direction. There is honeycomb structure. There is a different type of reinforcement like glass, and inside there is polystyrene foam core. So a lot of different materials were brought together to achieve the best performance out of this application, the sailboard. So usually Kevlar is used in body armor, and we are seeing inside the body armor there is Kevlar fibers that are woven, sandwiched with plastic films that are providing excellent protection. So what are metal matrix composites? As the name implies, you have metals, and you have metals as the matrix. This can be aluminum, lithium alloy, magnesium, copper, titanium, and other super alloys. And the reinforcing fibers are basically graphite, aluminum oxide, silicon carbide, boron, and molybdenum and tungsten can be the fibers. So basically, compared to polymer matrix, the advantages is higher modulus, toughness, ductility, and higher resistance to elevated temperatures. But metals are heavier compared to polymers. So, and it's also difficult to manufacture composites with a metal matrix structure. So some images of different metal matrix composites are given. And in this table, it is summarized to us what type of fibers are used, what type of matrix is used, and therefore what type of properties we achieve, right? So for titanium, boron reinforced titanium, jet engine fan blades. So we are seeing different applications like graphite reinforced magnesium, space and satellite structures. So super alloy as a matrix reinforced with silicon carbide, molybdenum tungstite. These are high temperature engine components. So of course, again, depending on the application, it will determine what type of properties what we want from the material, and by combining these matrix and fibers, we can obtain those properties. So in this image, we are seeing aluminum matrix composite brake caliper. This one is made using nanocrystalline aluminum fiber as the reinforcement in aluminum matrix. So this provides lightweight and then it provides, of course, weight savings when you use these in vehicles, because traditionally these brake calipers are made out of cast iron, which is heavier. So if you go back, actually see this table, for an automotive brake caliper, we are seeing the fiber in the matrix composite properties. So if look at the aluminum fibers, strength, modulus, and density. When we mix them with the aluminum matrix, we are seeing how the properties changes. Of course, aluminum fiber itself has a higher strength and tensile strength and modulus. When we combine it with a matrix, this is lowering, but then it is in average between the matrix and the fiber properties. So ceramic matrix composite, as the name implies, these are matrix is ceramic, which provides resistance to high temperatures and corrosive environments, but of course lack toughness, it's brittle, and matrix can be silicon carbide, nitride, aluminum oxide, and carbon matrix composite. These are famous for their ability to be able to retain their strength up to very high temperatures like 2500 degrees C. Fibers can be carbon and aluminum oxide, jet and automotive engine parts, deep sea mining equipment, pressure vessels, structural components, cutting tool and dies. Watch the videos I showed you in the canvas. Those are showing you how F1 cars are made out of carbon matrix composites to achieve lightweight. This figure shows us composite content in selected commercial aircraft as a function of time. and how we basically time keep increasing the composite content of the aircrafts. So in summary, composites are important class of engineering materials. We can have plastic, metal and ceramic as the matrix, which are used mainly in aircraft, aerospace and transportation industries, sporting goods and structural components. Fibers can be glass, graphite, aramid, boron, and which these polymer matrix composites can have high strength to weight ratios, high stiffness to weight ratios. In metal matrix composites, the fibers can be graphite, boron, aluminum oxide, silicon carbide, molybdenum, tungsten, and the matrix can be aluminum alloys, magnesium, copper, and titanium, and superalloys. In ceramic matrix, the fibers are carbon and aluminum oxide, and the matrix usually is silicon carbide, nitride, aluminum oxide, and carbon. So very important to understand how we put these materials together, in what shape, what structure, and what are the reinforcement fiber size, length, what are their volume percentages, and if you have a good strength in terms of the bonding in between the interface of fiber and the matrix. So orientation of the fibers in matrix. Many of these properties are affected by in what configuration and morphology you mix these fibers and matrices, or the reinforcing material and the matrix. That's it, guys. So see you next week, okay?